Okay, so we have a question right here. So diagram shows. So we have a diagram. So what this diagram says? So we have an increase in energy. It makes sense. This energy is smaller, and this is bigger in energy. So increasing energy means for energy level 2, energy level of 2, 3, 4. This should be 3 here. This must be 3. So 2, 3, 4 means energy increase. You can see this energy is smaller. This is bigger than biggest. So now, what do they say here? Do the transition indicate? Do the transitions indicate in the diagram lead to the absorption or emission? Okay. Excuse me. So now we say, look here, man. So this is energy increase, but this way is transition of energy. So this is not transition of energy. They just say, according to this data, this is bigger compared to this to that one, but the energy is moving down. Know what I'm saying? Like in the diagram, this is energy which is moving, but this is an energy increase. But now, look here, show the transition of electron. The electron move from energy level 4 to energy level 2. See what I'm saying? So it moved from this energy level to this energy level. So what do they want? They want do the transition indicator diagram lead to absorption or emission? It's gonna be emission. Means this energy level is gonna move from here to here. So some energy is gonna be emitted. Do you understand what I'm saying? Means some energy has to be released to reach here. So now we go for the second one. So the first is gonna be emission. It's gonna be emission. That's 11.2.1. Next one, talk about the frequency of the photon produced when the electron is excited and make atom transition from energy level 4 to energy level 2. So now the electron, let's move from here to there. Now they want us to find their frequency. So you're going to do the very simple formula. The formula say, very simple formula, excuse me. Very simple formula. So the formula say, about that frequency of the photon. So first and foremost, man, let's find the energy release phase. Energy release. So to get energy release, okay, energy release, we take energy at 4 because the electrons move from energy 4 to energy 2. Look here, direction of the energy was moving from energy 4 to 2. So energy 4 minus energy 2, and this is going to be 2.044 times 10 negative 18 joule minus energy 4, which is 1.635 times 10 power negative 18 joule. Now the energy which is going to be emitted is going to be equal to, plug in a calculator, which is going to be 4.09. So it's going to be 4.09 times 10 power negative 19 times 10 power 19 positive joule. Means, so what you should do, look here, excuse me, look where your energy is moving. So you take your initial energy, which is bigger energy when it started, but now, excuse me, mean this is energy which is smaller, and then we have another energy. So find the difference, and that's going to be energy which is emitted. Do you understand what I'm saying? Okay, so that's good. And another thing also for photoelectric, meaning when the energy moves from the excited energy level to the end, means photons has to be released. So when you say photons has to be released, means the energy has to be released or has to be emitted. So you gotta remember that, right? Okay, so now we say, so we have to take this one, and then because photons are gonna be released, means some energy. So this is the energy which is gonna be released in this case, which is photon. Now we come. Now they don't want the energy released; they want the frequency of the photon produced. So the energy released in photoelectric, sometimes we call it photon. When this electron move from this energy level to another energy level, by energy means photons gotta be released. So when the photons gotta be released, or photoelectrons, sometimes they call photoelectron. That's to say, when energy, okay, what are the frequencies of the photon produced when the electron is an excited state, makes a transition from energy 4 to 2. So when this electron move from energy 4 to 2, means some photons. Photons like sometimes they call photoelectrons. Like a light is going to be emitted. So when this emitted means going to be energy loss. So how are you going to get energy loss? Take this energy from where it started minus where it goes, and then that's gonna be our energy or we call photons, which energy could be emitted. But that's not part of the question. The question is to calculate the frequency. So you're going to use this formula. Say energy equal to hf. Energy equal to hf, and then h is the Planck's constant. So we're going to plug everything we have. Now we go energy we have. The energy emitted is going to be equal to 409 times 10 power 19. Our Planck's constant is always constant, which is 6.63. Is always constant h. This h is given there. If you look at the back of the formula sheet, it's always there. Okay, negative 34 times frequency. So this one also is there at the back of the formula sheet. So what you do now, you can get half f by making a subject. So what I'm going to do, I'm going to divide throughout by 6.63 times 10 power negative 34. 6.63 times 10 power negative 34. This is this concept. So frequency equal to this one. You take this one, divide, and then you divide, you're going to get 6.17, means you're going to divide these two. It's going to be frequency equal to, which is going to be 6.1710 14 hertz. So this is going to be the frequency. This is going to be the frequency when the photons move from energy level 2 to 4. And remember, when the electron move and it transits from here to there, some photoelectrons has to be emitted. And when photoelectrons will be emitted, this is going to be the frequency of those electrons. So that's how you do this question. Okay, just a little correction, right? This is negative 19, and this must be negative 19. So you divide, this must be negative. It's not possible. Negative 19. So I'm saying, so changing energy when the electrons, like this electron move from this energy level to the last energy level, photons going to be released. So some photons or photoelectrons, photons, or sometimes they say photoelectron, electrons, photons or photoelectron, which has like a light. It's going to be released there. So when released means you're going to get energy of 4.09. So what you do, take the initial energy minus final energy. You see, and this is going to be photons, energy of photons. So now they want the frequency of photon. How are you going to get frequency of photon? Say energy equal to hf is at the back of your formula sheet. Energy, because they want frequency. So okay, so for that case now, energy I have hf. Plug it in there, and you got it, man. So that's how you do it. So now, yeah, okay. So first of all, I want to explain to you how the photoelectric works. This photoelectric works. Look here. If the rays, so this is photoelectric, how it look. Do you understand what I'm saying? So when they start to explain here, this is how it look photoelectric. Let's say you have a ultraviolet light. The light comes in here. So we have a cathode and anode. Cathode is negative charge and anode is positive charge. So when the ultraviolet light comes in, it's going to strike at the cathode. After striking at the cathode, if this ultraviolet light have a higher frequency, so means if this frequency is bigger compared to the frequency of the metal plate, because here at the cathode, we're going to have a metal plate. So metal plate, it could be aluminium, it could be silver, it could be anyone, sodium or anything. So if the frequency of ultraviolet light is going to be greater than the frequency of this metal plate at the cathode, then meaning this has a higher energy. And if it has a higher energy, means it's going to strike it here at the cathode and it's going to cause the photons or photoelectrons to be released. And those photoelectrons are going to move from cathode to anode. And the moment they're going to reach at the anode, and then instantly the current is going to start to flow this way, because current always go opposite to the direction of electrons. So electron move this way, so current is going to flow opposite. That's why we put here positive. When the electron go this way, current always go opposite. So that's how photoelectric works. Okay, let me say it again. If you have a light comes in, so light always comes in here and they strike at the cathode. This is the cathode. So if these rays has a higher frequency, when you say higher frequency means obvious energy is going to be bigger. Frequency energy is like direct proportional. Means if this frequency comes here and it has a high energy, if it's high, okay, I'm going to say this. So this metal plate here at the cathode, you see this metal plate, it also has a frequency. So if this frequency of the cathode is less than frequency of light which is coming, then yes, means this frequency is bigger than this. So if this metal plates must have a frequency. So let's say it could be aluminium, sodium. So if this ultraviolet has a higher frequency, in other words, it has a higher energy compared to the frequency of the cathode, or in other words, it has a higher energy or higher frequency compared to this energy at the cathode or frequency of the cathode, then electrons gonna be emitted. So electrons gonna start to move this way now. You see that's why I put arrow here. They're gonna move from cathode to anode. The moment reach at the anode, the moment reach is gonna start, current is gonna start to flow opposite direction to the direction of the electron. So electron move this way, current is gonna move this way. That's how we test it here. So that's how photoelectric work. Okay, so you come to the situation sometime where this rays comes, but when this ray comes, their frequency and energy is the same thing. Their frequency is not bigger as the frequency of the cathode. If it's not bigger the frequency of the cathode, meaning electron is not going to be produced, and we don't call it electron for this case, we call photons or photoelectrons. They won't be produced. So for that case, if photoelectrons or photons, sometimes they call photons, if they won't be produced, means there won't be a current which is flowing. So that's a simple concept. So I'm saying another thing, one more. You come to the situation where this ultraviolet light has a frequency energy and is equal to the energy of the cathode. When they are equal, when the frequency of the ultraviolet is equal to the frequency of the cathode, or energy of ultraviolet, when you say frequency, energy, the same thing. Energy of rays which are coming, mean these rays coming, and energy of the cathode are equal. What happened with the electron? Meaning the electron here is, this ray is going to strike at the cathode, and then when it strike at the cathode, the electron is going to get excited. You got to use the same word, it's going to get excited, but it won't be able to move from cathode to anode because it won't have enough energy. Do you understand what I'm saying? But only when the frequency of light which is coming, or energy of light which is coming, is equal to the energy of the is equal to the energy of the cathode. It means the electron here at the cathode is going to get struck by these rays, but they won't be able, they're going to get excited, they're going to be struck, they're going to get excited, but they won't be able to move to the anode because the energy of frequency coming, frequency of the ray coming, and frequency of the cathode are equal. So three things quickly. When frequency of the ray is greater than the frequency of the cathode, or is greater, means when this ray is going to strike at the cathode, this cathode, the electron here, the metal plate of the cathode, the electron here, the metal plate, is going to get excited and it's going to start to move. Because why? This frequency is so big, it's going to be emitted in another way, and it's going to start to move from cathode to anode. And the moment we reach the anode, the current will start to move in the opposite direction. Electron and current move in the opposite direction. In second case, I say when the frequency of ultraviolet light is less than the frequency of metal plate, meaning no electron is going to be emitted because already this frequency is less. But another situation when the frequency is great, is same frequency of the light, the same as the frequency of the metal plate or energy of the metal plate, meaning the electron here is going to be excited here at the metal plate, because which electron move? The electron of the metal plate is going to get excited, but it won't be able to move from here to the other side. So the only time we have a kinetic energy is when the frequency is bigger, because when anything moves, you're going to have a kinetic energy. So when the frequency here is bigger than the metal plate, means the electron is going to move. So for that case, we're going to have a kinetic energy. So that's it, man. So now let's go to the second question here. So I'm going to rate this part here, man. This is called photoelectric. It's not part of the question. So now let's go here to this question here. Excuse me. So let's say the threshold frequency, what is the threshold frequency? Threshold frequency is the frequency here at the metal plate, which you call F0. See, that's the threshold frequency. So let me write formula for you quick. So before we do this, say threshold frequency has this one. Can go the kinetic energy of most energetic electron ejected. So for this case, if the electron were ejected by any means the frequency of these rays were greater than the frequency of the metal plate at the cathode, because they say electrons were ejected. Electrons were ejected. If electrons were ejected and photons were produced, and these photons like a light were produced here when the electrons were ejected from the cathode to anode. So we're going to say, okay, so now let's go now. We're going to say, okay, so let's write the formula. So the formula that we're going to use, we're going to say energy equal to threshold weight done plus kinetic energy. So this threshold frequency, okay, let me explain to you. Okay, if this light, I'm going to explain again in mathematical now. If this light comes and then this light has a higher frequency, means the electron is going to be omitted, we know, or photon is going to be omitted from cathode to anode. If it's omitted, means we're going to have a kinetic energy because they're going to be moving. But the second phase, we say second place, we say if this frequency is less than the frequency of the metal plate, means we're not going to have a kinetic energy. Why? Because it won't be able, it's going to strike, but it won't be able to make this electron of the cathode to be excited and move to the cathode. So we don't want to have this. When this frequency is less, we don't want to have a kinetic energy because the electron will not move. The third case, we say when these rays come and is equal to the metal plate. When it's equal, the electron is going to get excited, but it won't be able to move. See? So for that, do you understand what I'm saying? So also we're not going to have a kinetic energy. See what I'm saying? We're not going to have a kinetic energy. Okay. Now let's go to the question. Let's go to the question. Now they say, so now we know for this case, they say electrons going to be produced. What do they want? Now calculate the kinetic energy. So this is what we want. Easy. So that's what we want, kinetic energy. So we're going to say, what is energy? Energy is... Alright, so something very important, right? So for the most case, every time when you do this question, make sure you have to compare the frequency of energy of a light and also compare with the metal cathode. This frequency, it has to be very big so that when it strike here, the electron is going to be emitted and the electron is going to move from cathode to anode. But so now let's say I use calcium, let's say I use sodium now, sodium cathode, which has, let's say, less frequency compared to the frequency of a light. Means electrons going to be omitted and the electrons can start to move from cathode to anode, and now current is going to move opposite direction. But so now when frequency of a light is bigger, you see I say frequency of a light is bigger than threshold frequency. So threshold frequency is the frequency of a metal. So threshold frequency is the frequency of a metal. You know what I'm saying? And when you say threshold wave done, so this is called threshold frequency. Frequency of a metal at the cathode. Or you say this is a minimum frequency that you need for you to omit the electron toward the anode. Okay, this W naught, this we call threshold wave done. This is a minimum wave done we need so that the electron can be omitted from the cathode to the anode. So now, if this frequency which is coming is greater than the threshold frequency. What is the frequency of the metal? Means obvious, the electron is going to be omitted from the cathode to the anode. So in other way, if the electron is going to be moving, means you're going to have a kinetic energy. So that's why we use this formula here. We say energy equal to the ratio of wave done plus kinetic energy. What that means? Energy means energy of this light is going to be equal to threshold wave done, means the minimum wave done or the metal plate to omit electron plus kinetic energy. Why plus kinetic energy? Because when energy strike at the cathode or frequency strike at the cathode, means the cathode is going to get excited, and when it gets excited, electrons go start to move from the cathode to anode. That's how we're going to use this formula. When frequency or energy is greater than threshold frequency. That's what's here. Energy, frequency greater than threshold. We're going to use this energy. Now, you come to the situation where, excuse me, the frequency normal is equal to the threshold frequency. When it's equal, means the electron at the cathode, at the metal plate at the cathode, is gonna get excited. Look, it said the same word, it's gonna get excited, but it won't be able to move electron from cathode to anode. So for that case, we're not gonna have the kinetic energy. That's why I say we're gonna write the same formula, but here kinetic energy equal to 0. Means you're not gonna have a kinetic energy when frequency of energy equal to threshold frequency. The last one, what happens when this energy frequency is less than threshold frequency? Means this threshold frequency is bigger. So for that case, energy is gonna be insufficient. You see? No. The energy is greater than cathode. Means if the energy is greater, it's gonna be greater than threshold work done. So if it's greater than threshold work done, means this metal plate won't be able to release electron to the cathode. So first and foremost, make sure you look the frequency of the light and the frequency of the metal cathode. So now let's check here, for example. Now let's say here the threshold frequency of the Q is so we have a metal Q. We don't know what the name of it could be. Q equal to 4.4 times 10 power 14. But first of all, if we know the threshold frequency of this metal plate, we need to compare with the threshold frequency of the energy which is coming. But we did on the first question, which we got on the first question, which we got. Okay, I'm going to remind you quick of the first question, which it was. We say the first question, it was threshold frequency of the light on the first part, which is 10.2.1. So 6.117 times 10 power 14 hertz. So I'm saying, okay, let me remind you how did I got it so that you know how I got it. So the first part, we want to get the threshold frequency of the light. So how are we going to get the threshold frequency for light? Because now here, so I say energy equal to HF. But energy I know because the electrons move from here to there. So I find the difference between this and this. When I subtract it, I got 4 for energy, right? 4.09 times 10 negative 19 equal to H plus potential goes constant 6.3 times 10 power negative 34 plus constant times frequency. So this will be frequency of a light which were coming. So plug in a calculator, divide by 6.63 times 10 power negative 34. So the 6.63 times 10 power negative 4. So frequency of a light which were coming, we had it already, which was 6.17 times 10, 14 hertz. So these were the frequency of a light which were coming. So now they say you have threshold frequency of metal, which is 4.4 times 10 power 14. So now you try to compare now. The threshold frequency of a metal is 4.4 times 10 what? 14 hertz. Threshold frequency of a metal Q. But now the of a light which you did in the first party, this is a metal Q. But of a light 6.17 times 10.14 hertz. So now we say, since this frequency of a light is bigger, so electron is going to be emitted. So it's okay, no problem. We don't have a problem. So let's calculate. It's going to work because the threshold frequency of the light which were coming, which we calculated in the first part, seems to be greater, 6.17. So it's okay, no problem. But if it was less, and then no electron is going to be omitted. If it was going to be equal, and then we say electron was going to get excited at the cathode, but it wouldn't be able to release electrons. So now for this case now, excuse me. So I'm going to write this part here. So we say we're going to apply the formula now because you know the frequency of light is bigger than the metal cathode. So we're going to apply the formula. Energy equal to threshold work done plus a half what kinetic energy mv square. Now what do they want? Calculate the kinetic energy. Means we need this, and of course we're going to have, because this frequency is bigger than the metal cathode. Okay, what is the energy? Means this is the energy of the light which are coming in this ultraviolet, which we did already in the first part. On the first part, the energy we are giving. How did you get? We take this minus this, which we got already. It was formed when 0.9 times 10 power negative 19. Okay, threshold went down. This is like H times F naught. Okay, so we have our H. H is just H, Planck's constant, which equal to 6.63 times 10 power negative 19, if I'm not mistaken. Negative 34, apologies, negative 34. Negative 34. Plus constant. And then times our threshold frequency. Threshold frequency is given there. 4.4 times 10 power 14, power negative 18. Okay. And then plus kinetic energy. This is kinetic energy. So what you do, you can take all this group multiply, get the answer, take at the back, take all this minus this, and then you're going to get your kinetic energy. So my kinetic energy here is going to be equal to, plug that in the calculator, plug that out, and then you're going to get 1.17 10 power 19. So it's going to be 1.17 times 10 19, negative positive, let's see, negative 19 joule, negative 19 joule. So this is going to be energy. You know what I'm saying? For now, let's go for the second one. Now they replace this metal. Means they say, okay, let's take this metal out. We don't want to use that metal. And then when they take that metal out, they put new metal. Which metal? They're going to put metal iron. So since they put new metal, so you should have to look again for the frequency. Frequency of this light coming and the frequency of the new metal plate. What are the frequency of a light? So frequency of a light we knew, like I say, in this one, which you have already at first. So frequency of a light, see, frequency of a light which are coming is 6.17, which we know from beginning for light. Excuse me. And threshold frequency of a new metal. What is threshold frequency of a new metal? Frequency of a new metal equal to 7.5 times 10 14 Hertz. So what happened now? Excuse me. So since the threshold frequency is bigger than the frequency which is coming, this is the frequency of a light. So if the threshold frequency is bigger, like means the frequency here is bigger compared to the frequency which is coming. So this frequency if is less, just like how we see it, because the frequency is less, look, 6.17, means this frequency is less compared to this 7.5. So this frequency is less, it won't be able to emit electron from cathode to anode. So no electrons can be emitted. That's the answer. No electron is going to be emitted. Why? Because the frequency of a light which is striking at the cathode, you can say that, is less than the threshold frequency at the metal cathode. So no electrons can be emitted, no electron emitted, electrons or photons emitted. Why? Because frequency which is coming is less than threshold frequency. Thank you so much for your time, man. Peace and love, man. Peace and light, man.